Okay, so we're going to talk about how to use backpropagation with recurrent neural nets. And here's the basic structure of a recurrent neural net. We have our hidden units, our functions of one another in this forward manner. And we want to take our gradients of our loss functions with respect to the various, of our total loss function with respect to the various hidden units. So one thing that we can see is that if we want to take a gradient with respect to some h sub t, then we have to worry about all of the possible ways that this h sub t can get connected to different loss functions. So of course this h t is input ultimately for L sub t's output, but it's also ultimately input for L sub t plus 1's output, or the L sub t plus 1, and so on. Right? This can the h sub t is input for all of the L sub t's in the future after that. So we have to take that into account. Right? So our backpropagation through time, the basic idea, and this is specifically for recurrent neural nets, is that we have our loss function, which is the sum over all of the losses. And so we want the gradient of the total loss with respect to, first of all, let's start with the gradient with respect to the logits, O sub t plus 1, or so O sub ti. Well, if you remember for the logistic loss, if we use the logistic loss, which is just our cross entropy loss, that if you have if you take the gradient of the loss with respect to the logits, then that ends up just being the probability, the predicted probability minus y. So this is something that we learned in logistic regression, and this can make our lives quite a bit easier just using this fact. Okay, so far so good. We haven't hit the h's yet, so we don't have to worry about any of this crossing over between different time points of the gradients. Another situation in which we don't have to worry about that is when we take a gradient of our total loss with respect to h sub capital T. Now, this gradient, h sub capital T, only determines that final L sub capital T. And so we can just think of the gradient of that L sub capital T with respect to h sub capital T, right? And that's just going to take this following linear form. And you have this linear form just because O sub T is a linear function of h sub capital T. Sorry, this should be O sub capital T. Capital T. Okay, so let's just double check this. We have O sub t is equal to this linear function of h sub t, and you have this V matrix multiplying h sub t. So that's why we get the V transpose there when we apply the chain rule. What else do we have? We have that our loss function here, this was this P sub ti minus y sub capital Ti, and that's very straightforward as well. Right? Okay, so far so good, but now we get to the complicated part. We want partial L over partial H sub little t for any arbitrary little t. Well, this H sub little t it's an input for H sub t plus 1. So we have to incorporate that. We have h sub t plus 1 over partial h sub t. There's that. Then we have to take, of course, the inner product of that with respect to the partial of L over partial of h sub t plus 1. And then we also have plus the partial. Now we also have our output at time t. That's also a function of h sub t. And we have this transpose our partial L over partial O sub t. Right. So this is our basic recurrence equation, and this is how we're going to take care of everything. This partial L over partial O sub t, well, that's just going to be another of these simple functions here, right? It's easily calculable. So this is easy to calculate. This is just going to be our V transpose again, just like before. These things, these elements here, this is the h sub t plus 1 is just a linear function of h sub t. So we're going to get another we're going to get another, or sorry, h sub t plus 1 over partial h sub t. It's linear with a tanh activation function. And so we also have to take the derivative with respect to tanh, but that's something we do with standard backpropagation. So for example, if we just focus on this, that's the partial over partial h sub t of the tanh of b plus w times h sub t, plus some other components, but those have nothing to do with h sub t, right? So that's equal to this w transpose, and then we have to take the derivative of tanh. That turns out to be the diagonal of 1 minus h sub t plus 1 squared. That's just what the derivative of tanh turns out to be. And so if we think about what star is in the end, we have that star is equal to our w transpose diag of 1 minus h sub t plus 1 squared, where square is element-wise, partial L over partial h sub t plus 1, which has already been calculated, plus our v transpose partial L over partial O sub t, which we've already calculated as well. Okay, so our backpropagation through time is just recursively apply star. That's what backpropagation through time is. So, that was actually pretty complicated, right? And you can imagine doing this for the bidirectional M, R and N is going to be even more complicated. But for the most part, this is something that can be coded into our frameworks, and it is. So, for you, most of our purposes, we're not going to need to code this up by hand. I just wanted to show you how this was possible and how the chain rule could be automated, even if we have this time dependence. Now, typically, in these neural machine translations, we don't just have a single sentence, thank God. We have many, many sentences, right? And each of these sentences is going to give its own loss function. Each loss is going to be the sum over the different losses, right? And so for how we combine each different sentence, well, we're just going to use each sentence to form our stochastic gradient update. And so we use backpropagation through time to form our full gradient for a given sentence, but that full gradient for a given sentence is just a stochastic gradient for the entire loss, which would be the sum of all of the losses. So this is where it sort of differs from just applying a time component, treating our entire data set as a time series. When we're talking about neural machine translation and most modern neural net applications, we actually have repeated observations of these time series type dependent structures. So that's a big point that makes this it tractable to actually train these methods.